Welcome back, my friends. So we're going to jump into another Kurzgesagt video because he just posted a new one and it looks friggin' awesome. It looks right up my alley, so let's do it. Before we get into it, I just want to say a big thank you to everyone who's using my software. If you're new around here, I've just created this brand new type of VPN. It's called a post-quantum VPN. It can protect you guys from quantum computers. It's called CalVPN, and you can actually go use it for free right now. We have a free alpha out. It's only on Windows, there's only one server, but there's a beta coming in about 3 weeks now, and that's gonna have a bunch of servers. It's gonna be on Linux, Mac, etc. We have about 500 users now and everything seems to be going pretty smoothly, so that's really exciting. So if you've been following the Cal journey really quickly, the roadmap to the beta, there's 3 more things to do. We just finished making the UI, it looks pretty cool. We'll make it prettier and we'll come back to it, but next up is to add all the server locations. There'll be a button, so you can change the location. Then after that, we got to implement a subscription system, put an account button in the top left. And then finally, we have to do all the app conversions, for Mac, Linux. All of that stuff is actually fairly quick because I'm moving pretty quick. Just heading off into a wrap right there. Anyway, the final thing to mention is not a wrap. I'm also running this daily newsletter called The Daily Dance, and we break down all the latest science news in a very short little form. Like, takes a couple minutes to skim through it. You see what's happening in the science world. So if you like learning and keeping up to date with all the amazing, mind-blowing things happening literally every single day, come get the free email. I put a personal note at the start. It's always fun to write that. I always put, AI art at the bottom. I love creating that every day. It's like my therapy. So yeah, come get involved, completely free. Let's travel to the most extreme place in the universe. So the thumbnail for this said quantum foam. So this is going to be a very interesting video. Let's get into it. I can tell you all kinds of crazy stuff.
The universe is pretty big and very strange. Hundreds of billions of galaxies with sextillions of stars and planets, and in the middle of it all, there's Earth with you and us. But as enormous as the universe seems looking up, it seems to get even larger when you start looking down. You are towering over worlds within worlds within worlds, each in plain sight and yet hidden from your experience. Let's go on a journey. We'll start in a park about 1,000 meters long, enough for a 15-minute walk. Every time we click this magic button, we'll become 1,000 times smaller. Please slip into this magic science suit so you don't die and can still see. Ready? Let's go.
Okay, let's do it. The most extreme place in the universe, you say?
The miniature realm. You are the size of a grain of sand, just 2 millimeters high, standing on a blade of grass that seems as tall as an 8-story building to you. A square meter of lawn is now a dense metropolitan area with 100,000 blades or 2 Manhattans worth of grass towers. From your new tiny perspective, the park that you could quickly stroll through before is now the size of France. Crossing it would take at least a week. Human-sized humans loom over you, 4 times taller than the Empire State Building, their steps falling from horizon to horizon. A bee the size of a helicopter lands near you, making the ground shake as its hairy carapace vibrates with each wing beat. You try to escape, but are barely able to move because the air is so gooey. Before you clicked the button, air resistance was barely noticeable, but as you're now 1,000 times smaller, it's as if the air has become 1,000 times denser. It feels like you're moving through honey. Flying insects like bees use this to their advantage. Their wings are not made for gliding, but like paddles that row through the air. Scaled up to human size, the bee would outrun a Concorde jet, except it couldn't even take off because it would be too heavy for its wings. The Microscopic Realm. You've entered the Microscopic Realm and are now less than 2 micrometers tall, about the size of an E. coli bacteria. From your new tiny perspective, the park you started in is now 1,000,000 kilometers wide to you. If you walked non-stop, it would take some 25 years to cross it. It's hard to grasp just how huge the microscopic world is to its tiny inhabitants. The giant bee that was close a moment ago is now the size of Mount Everest, towering high into the sky, but alive, humming and vibrating. The air here feels
That's such a cool visual.
almost solid to you. On the human scale, it would be as viscous as lava, extremely hard to push through. The blade of grass now expands so far you can't see its edges, stretching as wide as Paris would to a regular-sized human. You see valleys that look like dried-up riverbeds, dead patches like deserts, and giant craters left behind by voracious aphids. But if you look closely, this is not terrain. These are rows of individual cells, each the size of a house with hard exteriors like glass shells. Every few cells there are huge openings called stomata, like mouths sucking in air and blowing out oxygen. Suddenly, the gigantic bee begins to move. A construct made of rigid pieces that slide against each other like a suit of armor. It takes off to escape a drop of water the size of an asteroid that fell from another blade of grass and is now rushing at you at breathtaking speeds. You brace for impact, but instead of feeling a strong punch, you just get sucked in. You try to swim, but the water feels thick and stiff.
This video is brilliant because like people are not going to go anywhere. They'll want to see what's going to happen, right? Because they're just doing such a good job of storytelling.
And holds onto your limbs like glue. Air molecules are free spirits, while water molecules act more like social creatures that group together whenever possible.
So I'm not commenting too much because like I want to get to the quantum foam stuff and talk about that.
Pull on each other and create a relatively strong cohesive force that traps you. You can't help it, but you're still moving, tumbling in all directions, helplessly dragged along by an invisible current. Floating in this miniature lake are tens of thousands of microorganisms. They take on many forms. Viruses the size of tennis balls float around you aimlessly. Others, like Euglena oxyuris cells, pass you like freight trains. But most look like oily jellyfish the size of a car, sporting long tentacles that act like supercharged propellers. Despite the water holding onto them like glue, some move hundreds of body lengths per second, equivalent to a person shoveling through mud at over 600 kilometers an hour. However, bacteria weigh so little and water is so viscous that they basically have no inertia. There is no gliding on this scale. The result is a weird, jerky motion that's hard to keep track of. Maybe we can learn more about this strange motion if we go even deeper.
So cool. If you read the Daily Dance, you would have seen, I think it was yesterday, we mentioned how we've just discovered a bunch of smaller microbes that are completely new to science that we've, haven't documented.
The molecule realm. You've become the size of a molecule, just under 2 nanometers wide. At your new tiny scale, the droplet now seems as big as the moon to a regular human. The blade of grass it rests on could reach from the tip of Alaska to the end of Australia, and the park is now almost the size of the solar system. But instead of mostly empty space, it is filled with stuff. Everywhere you look, there are innumerable of molecules and atoms. The rigid walls of the grass cells beneath you are clearly vibrating, rippling with waves of energy. The water droplet contains nearly a sextillion water molecules that are all in motion. Water is actually a storm of H2O molecules smashing into each other hundreds of trillions of times a second. Each of them is moving at speeds of around 2,300 kilometers an hour and bombard their surroundings mercilessly, sending small objects hurtling in all directions. This is the source of the invisible current that you noticed when you were 1,000 times larger.
Is anyone else just thinking right now, like, what an astonishing universe? We're not even close to, we're going to go way smaller. But thinking the opposite way, how big things get. Imagine if everything we can see, the observable universe is just like a small fraction of something much larger. It just is so incredible to think about.
Scaling this speed up to the human scale is impossible, as a human-sized molecule would be 2,000 times faster than the speed of light. All this furious motion comes from heat. Heat is a bit abstract at our human scale, where you touch something and get a vague sense of whether it's hot or cold. But down here, you really feel what heat is. The motion of molecules, vibrating, twisting and colliding as if they're inside a furious ball pit. When these molecules lose heat, they move more slowly and collide less often. They gain heat, they speed up and smash together with renewed fervor. Temperature is basically the measure of the average speed of these fantastic dancers performing all day. Suddenly, a molecule hits you especially hard, and you're catapulted out of the water droplet into the air again. And here, you see something unexpected. The stuff between the air molecules. Nothing. Between the molecules that make up the air, there is a vacuum. On average, a molecule in the air travels for about 60 nanometers, which is about the length of a hockey rink if it were the size of a human. If we were to compress all the molecules and atoms buzzing around in the room you're watching this in, they would only fill about 0.1% of its volume. 99.9% of the space around you is a vacuum. You just don't notice it. Which also means that every time you take a breath, you breathe in mostly nothing with a few atoms.
Did you know that every time, there's so many atoms in every breath you take. Every time you take a breath, you are literally breathing in atoms that Hitler breathed in, that dinosaurs breathed in, everyone who ever lived, there's an atom that they breathed in, you're breathing in right now. You might feel violated, but it's also actually quite comforting, because if someone close to you has passed away, isn't it nice to know that some of their influence on the universe is still around, and you're literally interacting with it every time you take a breath? You can't escape their influence in the rest. You won't be able to for the rest of your life. Every single breath, you'll breathe in stuff that they breathed in. And I think that is absolutely beautiful.
The subatomic realm. At your size of under 2 picometers, scale starts to lose its meaning.
That's small.
A human would be nearly 2 billion kilometers tall relative to you, so large they could stretch their arms from the sun to Saturn.
Yeah.
An atomic nucleus would be the size of a grain of sand you could hold on the tip of your finger. That grain holds 99.97% of the atom's mass. The rest, a sphere of influence about as large as the Eiffel Tower from your perspective, is filled with an electron cloud. That's basically all the places where electrons might be at any given moment in time. Electrons are shapeshifted outside a nucleus, creating a new and vibrating mess of different shapes with every new moment. Unlike the graceful motion of planets, the atomic nuclei are chaotic blurs. Like the graceful motion of planets, the atomic nuclei are chaotic blurs. They bulge, roll, quiver, and breathe.
Is he going to mention the craziest thing they do? Well, maybe not the craziest, but quantum tunneling. They just literally disappear and then appear on the other side of like a brick wall. Like the equivalent is like getting a tennis ball, throwing it at the wall, and it just goes through the wall. Atoms can literally do this, and a lot of our electronic devices even rely on our understanding of this. But anyway, then the other thing they do as well is quantum entanglement, which is what those 3 super dudes just won the Nobel Prize in Physics for just yesterday. So we'll see if he touches on entanglement. Otherwise, we'll save it for another day. But yeah, how awesome is that? The Nobel Prize to the spooky science of entanglement. Love it.
They hold back the same energy that powers nuclear bombs, and it doesn't let them sit still. They twist and vibrate sextillions of times a second.
Okay.
It's time to end our journey and return to... What you doing? Stop it. The smallest place...
Malfunction.
We have reached the bottom, the border between reality and unreality. The scale here is the Planck length, which is the distance light travels in a Planck time. Planck time is the time it takes light to travel a Planck length. Okay. None of our models of the universe make sense at scales smaller than this, so for now, this is it.
So let me give you a simple thought experiment that kind of demonstrates why they don't make sense at this sort of scale. And I gave this thought experiment in the string theory video, so I'll word it it's a little bit different in case you didn't really get it that time. So yeah, go watch that video if you want way more on this stuff. But basically, let's say that you're trying to look at some region of space and time by putting it under a microscope, right? Well, by the uncertainty principle, you know that you have to put higher and higher energies into a smaller region of space in order to, probe what's going on at shorter and shorter distances. So you need smaller and smaller wavelengths in order to resolve what's going on at small scales. And smaller wavelengths means higher frequencies, right? Higher frequencies means you have more energy. That's another way of saying it by quantum mechanics. And so this is, why we need to build giant machines. It's the irony that we build these huge accelerators to probe really high energies to look at the tiniest distances that we've ever seen in trying to see what's going on with the laws of nature at very short distances. Now, in a world without gravity, all you need to do is go to higher and higher energy extremes and probe smaller and smaller distances. But in a world with gravity, something really bad happens, right? Eventually, you put so much energy into such a small region of space. When you put a lot of energy there, because E equals mc squared, it's like putting more and more mass there, right? So at some point, you've got so much mass in such a small region of space, you're going to collapse that region into a black hole. And that makes it impossible to see what's going on in there, right? So, you get frustrated, you try and build a, bigger machine, higher energies, you build an even bigger black hole. So that means there's no operational meaning. So it means there's no operational meaning to talking about distances and times that are smaller than, 10 to the minus 33 centimeters and 10 to the minus 43 seconds, these Planckian scales, right? And every time this has happened to us in physics before, when there's some notion we can't even, in principle, give operational meaning to, it means that idea is approximate, right? It has to be replaced with something else. In this case, it's pretty dramatic because the thing that's approximate is the notion of space-time itself. So when do these things hit you in the face? Well, when the curvatures in space and time become comparable to the Planck scale. So for instance, if you run the pictures of the expanding universe back in time, you run into the Big Bang singularity, right? And what's going on is that as you get closer to the Big Bang, the curvature becomes comparable to the Planck scale, right? So the very notion of space and time is breaking down there. And that's why we don't know what's going on at the Big Bang or before the Big Bang. Even the word before breaks down when you get close to it. And if you throw yourself into a black hole, there's no center where you get sucked into, but there's a sort of moment of time in your future where you get crunched. It's like the opposite of the Big Bang. It's the big crunch inside a black hole. And, again, at that moment, the curvature becomes comparable to the Planck scale. And so our theories just break down when gravity is strong and quantum gravitational effects are dominant. I didn't mention this in the other video, but there's also another aspect of this. It's kind of like the end of reductionism.
We think that down here, particles bubble into existence and then spontaneously disappear, creating a quantum foam of unimaginable energy. Can we go even smaller? We don't know. It's time to return. If you look up, the universe is large and strange. So incredibly large and strange. But if you look down into the tiny and extremely tiny, the universe seems even larger and even stranger. In the end, the perfect place might be where you are right now. Not too big, not too small.
So let's talk about this quantum foam stuff. But to do that, we have to talk about virtual particles, because basically the quantum foam is basically just like a bunch of it's a population of virtual particles, right? Popping in and out of existence, bubbling. But there's problems with this. So let's talk about virtual particles for just a second. So virtual particles, right? In principle, just mathematical artifacts invented for calculating interactions between particles. I just want to emphasize that these virtual particles are not a different category of particles. But anyway, so the way we calculate interactions between particles are with Feynman diagrams, right? And I'll put one on the screen. So the external lines you can see, they're basically particles we can observe, right? So in this case, you've got an electron and an anti-electron, which is a positron, coming in from the left. And then on the right, you've got a quark, an anti-quark, and a gluon coming out. I should say the time axis is going from left to right, right? And the thing you can see in the middle, the squiggly line, they're the virtual particles. They go in the middle, right? And in this particular case, it's a photon. But there's many other possible diagrams for this interaction, actually infinitely many, all right? And each diagram actually has a different set of internal lines with different types of particles represented by, by each line. But these virtual particles are of just the same type as, the regular particles, photons, electrons, quarks, whatever. So just to summarize, we only see the particles coming in and out of the diagram, right? We don't know what happens in between. And we approximate that using Feynman diagrams and the concept of virtual particles. So, something fun. So you know how I said for each interaction, there are infinite possibilities for virtual particles on those internal lines, right? Well, if they exist, then all infinite possibilities must exist at once in a quantum superposition. If your mind isn't blown just yet, it gets crazy. So empty space, right? If you had space, it contains nothing. No energy, no charge, no matter, nothing. We say there's an active population of virtual particles that, physicists call the quantum foam, right? With bubbles appearing and, coming in and out of existence. So at the subatomic level, right, space in this view is never actually empty. So these bubbles in the quantum foam are quadrillions of times smaller than atomic nuclei, right? And they last for infinitesimal fractions of a second. Or in quantum speak, the size of a Planck length for a Planck time. So if this sounds like BS to you, Well, let's talk about observations, right? The first one came from tiny disturbances in the energy levels of the electron of an hydrogen atom. A second effect was predicted in like 1947 by Casimir and Polder, and they realized that if the quantum foam was real, they reasoned that, you know, these virtual particles should exist everywhere in space. And they went further, because particles also have a wave nature, there should be waves everywhere. So what they imagined was to have two parallel metal plates, you know, right next to each other, and quantum foam would exist both between the plates and outside of them, right? And because the plates were placed so close to each other, you know, theoretically you could only have short wavelengths in between, and you could have short and long outside them, right? And because of this imbalance, the excessive waves outside the plates should overpower the smaller numbers between, pushing them together, right? Well, 30 years after it was first predicted, this effect was actually observed qualitatively, right? You know, it was measured accurately, I think, in 1997. And so, yeah, the quantum foam is real. It exists. However, the idea of virtual particles, so in Feynman's way of thinking about things, you have these Feynman diagrams. All the evil has to do with this notion of a virtual particle, right? And as the language suggests, you know, these are kinds of like figments of theoretical physicists' imaginations. They're kind of things we're adding to our descriptions of the physics. Why? They're not real things that show up in our detectors and so on, right? They're just things we're invoking in order to be able to give the description of what happens inside there a consistent space-time interpretation, right? And so inside that, this particle, you know, doesn't go out to infinity. It doesn't come in from infinity. It propagates over a finite range in space and time, right? That's the virtual particles. And they're kind of a fiction, right? That's like needed to manifest the rules of space-time in quantum mechanics. So on one hand, these things are directly responsible for like all the horrible complexity at the deep end of physics. There's no two ways about it. And it's kind of funny, isn't it, that these exact notions are making space and time manifest. They're the exact things we need to somehow relax, you know, if we want to go deeper. And that's what people are trying to do, right? This is theoretical physics. We want to have like this second picture where we don't care about that, and we want to, you know, see other things. So the physical idea is to eliminate these virtual particles, never talk about them, never use them, and somehow get the answers another way, right? That's the physical idea that a lot of theoretical physicists are, you know, tackling. And I like this approach the most, right? This is just the thing where, you know, I'm getting into, there's no experimental evidence for this sort of stuff, but I'm just giving you my sort of, you know, opinion. Make sure you subscribe, come get CalVPN and use it for free. Come get the Daily Dance email, the free email, and I'll catch you guys next time. I really do think we're in a special period, right? You can think of most of the last 400 years. Well, the analogy is like, you know, the last 400 years were like, you got on a plane, you flew to Kathmandu, you know, you got out, you found some Sherpas, you started going through the foothills, and then after a long time, you're finally at base camp, right? On Mount Everest. The last 400 years have been about getting to base camp of Mount Everest, right? 2,000 years ago, 400 years ago, you could wonder about the deep nature of space and time. You could wonder about all these things, and it would be totally stupid and pointless, because 100 years ago, we didn't even know why the grass was green. We didn't know why water was wet. So it was really completely pointless to think about these things, space and time, and all the rest of it, right? We know the answer to those questions right now, and more esoteric ones, but the next questions, right? That's what you've always got to work on in science. The next question are these questions, right? They're not like 7 questions between them and the other ones. We're at base camp now. So what do we do? So you're at base camp, right? So what do? You can either sit there or wait for helicopters to take you up, or wait for some oxygen tanks, or you can start trying to go up. You know, maybe you'll fall off and die. Who knows what will happen? But you can start doing it. And that's hopefully what, you know, you take away from this little analogy. It's possible to begin climbing. Many people are climbing with different routes, and, you know, some are making more rapid progress than others early on, but they tap out at the end because they didn't, you know, use the right strategy. You don't know. So speculation is usually pointless, but it's fun. What a great video. That was beautiful. Make sure you subscribe, come get CalVPN and use it for free. Come get the Daily Dance email, the free email, and I'll catch you guys next time.